In the extreme instantly universe, there are very many unknown things. And especially the several things, possible some of the baryogenesis, and the other ones in inflation theory to explain some of the problems in the Big Bang theory. So there are some of the many problems in the Big Bang theory, and just now we talk about the two things, the possible flatness problem. From the first Friedman equation in the cosmology, we can parameterize the curvatures in terms of the density, and we will rearrange such equation. The curvature term k can be rewritten by the omega minus 1. And in the observable universe, in the current size, the curvature is almost zero, almost a flat universe, so the omega is almost 1. And from this factor, Hubble's parameters are a dash over the I, is that this factor is the 1 over the I dash square. And in the meta-dominant universe, the I dash is a decrease, because the scale factors are proportional to the t to the minus n and is of the number. So the a does the decrease, so the such a quantity omega minus 1 the increase during the cosmic evolution. It means that the t bit the omegas are almost similar to the one in the current universe. This quantity omega minus 1 should be equal to more precisely in the early universe. That's a very quite fine tuning, so it is called the Flatness problem. The second one is the some of the monopole problem not observed, but I will talk about some of the horizontal problem. The horizon size is defined as the difference of the conformal time. And the conformal time by the change variable under definition is the dt sort of the IA scaling boxes here, and change the variable we can change the integrals as a dln a over the ln ah. So we can interpret as the 1 over the ah is the conmoving Hubble horizon, such a quantity, and actually that is just the 1 over the I dot. And for the ordinary metric is the scale factor is the proportion to the t to the minus alpha. Alpha is just some of the positive number. So the a dots is the t to minus alpha minus 1. So the origin size is the increase during the ordinary matter. And but the darkened case, the scale factor is proportional to the exponential ht. So the a dot is the exponential ht proportional to the such a factor. So the horizon size, one of the h dots decrease during the cosmic evolutions if the dark energy is the dominant. So we can do the horizon size evolutions as a function of the time. In the meta-dominant case, the horizon size is increased, but in the dark energy dominant styles, the horizon size are decreased because the universe is too rapidly expanded. So and if we use this ordinary matter and dark energy dominant styles, then there's some of the problems that appears. If we detox some of the CMB, there's a CMB is a very strongly correlate. There's almost 2.7 Kelvin for any directions at any time. But if we calculate some of the correlations of the CMB, that's causally disconnected. So in the causal time directions, causal time diagram, the light cone for the one point of the CMB, it is actually this universal and the one point, and the other point. Correlation between them are actually disconnected causally. We can interpret that this the horizon evolution during the meta dominant, the horizon size is included, so that we can expect that the horizon size was just small in the initial conditions, so that it can not provide the causally connected for the correlate the CMB. But if we introduce some of the inflation, very rapidly expansion period, then we can extend the diagram with the causal time. There is additional period times in here. And we can extend some of the light cone line. Then such a point and other point is causally connected in the very early universe. We can do as a Hubble horizon evolution, one of the AIT, because the implosions are similar behavior sort of dark energy. So the Hubble horizon size decrease during the implosion stage. So we can expect that the Hubble size, horizon size was large at the initial condition, and this horizon size should be larger than the previous one to explain the CMB correlation. And if we calculate some of the CMB correlation, then how much the expansions are very large, and the ratios of the scale factors at the binary styles and linear styles should be the 10 to the 64 to beat the observed CMB correlation. So if there's the implications that both the Flatness problems and the correlation not horizontal problems that can be solved, and usually the implications as explained by some of the scalar dynamics, introducing sort of the additional scalars, so-called the Inflaton. Also, there are some other models like some of the Higgs indices or R-scale indices where the R is the Riemann tensor. Well, today so, I'll focus on the Inflaton's model. The simple actions for the Inflatons can be written by the kinetic terms and potential terms in the uh, volume element with the metric tensor. And the equation of the motions from these actions following from the potential term and the kinetic term. And one thing I want to mention is the minus Lucy, such a invariant volume element has also the dynamic cost. So if we assume that the spatial homogeneity, so the pi is position independent, then the remaining is a time derivatives term. And such a volume element, invariant volume element minus g of the root is a to the cube because there are three scale factors of the I scales in the spatial parts in the matrix, parallel W matrix. So if we use some of the Leibniz rule, there are two dot powers appear by acting the partial z partial g as the pi, and if we act this at the time derivatives on the invariant volume elements, then the pi dot appears then here. So there are two dot pi term and the pi dot with the Hubble frictions and the derivative of the potential. So it's a very similar looks to the as a harmonious Newton equation in the classical mechanics with the friction term. So Hubble terms as low as the makes the frictions of the scalar field, which is the prevents modulation. So if the Hubble friction term is comparable with the derivatives of potentials, then the scalar field is a law very slow, is called the slow law. So this pi dot terms can be replaced by the delta pi changes of the scalar field with the inverse of the h as the typical time scale. And if we assume the potentials is only quadratic term, then the derivatives of potentials are just given like that. And in the slow law, we can expect that the change of the scalar fields are very small compared to with the field value. So this similar equalities that are changes to the inequality. So the just the remaining terms is Hubble's and the quadratic coefficients of the potential as a master of the color field. So the slow roll condition becomes the Hubble parameter is larger than the mass of the Inflaton. The second one, so we can obtain another current from the symmetry, global symmetry, as a stress tensor. So partial mu pi with the G mu Lagrangian. and the both the 00 component energy densities as kinetic energy and the potential energy term and the produced, but the different sign for the potential term. In the slow roll condition, the such changes of the scalar field values are very small, so the pi dots are extremely small as compared with the potential. So the energy density and the produced has opposite sign, which is that kind of like as relative we discussed in the lambda senior model in the small Ruby. The famous potential shapes for the Inflatons is Bernoulli. So the in this ties the potential terms are dominant. Also in this ties the potential terms are dominant. So the Inflatons has a slow roll process, and in this ties the kinetic term pi does the dominant. So the oscillation. Pi starts oscillation. And during the discharge and the discharge, the inflations occurred, but if the inflatons go to the intervals of the potentials, so the inflatons start oscillations that is called the leading, which is the decay of the inflaton to the other standard model particle. So then there's the free heating, which is some of the rapidly decays of the Inflaton, so some of the standard models particles are produced at very earlier times compared to the rating. And there are some of the few remarks. The Inflaton's color field has some of the fluctuation by the quantum uncertainty. So the ending times of the relations are different, and they easy to make some of the curvature fluctuation, which is a source of the primordial perturbations that we discussed in some of the view before previous videos. And there are some of the constraints on the inflation model, several inflation model, some of the pi n, some of the power law of the scalar field, and the some of the R scale, which is the scale of the Riemann capacitance such model. And there are two variables, R and NS, as R is actually the radius of the some curvature perturbations and the tensor perturbation, and NS is some of the parameters that from the epsilon inflation model to make the rapidly expansion condition and observe the values nearby here, and we can constrain each models due to the observation value.